So here's a quick exercise. We are given this function. It's a surface, of course, v of xy, z equal f of xy. The function is x cubed plus x squared y cubed minus 2y squared. And what we need to do is we need to evaluate del f del x at 2, 1 and del f del y at 2, 1. This should be written evaluate rather than find, because we are looking for a value here. By itself, there is nothing here to do. It's pretty much straightforward. The key to remember is that we are holding one variable fixed and we vary the other. So before we evaluate at a point, let's first evaluate the derivative as a function. So what is del f del x? Okay, we hold y as a constant, so we have the derivative of x cubed is 3x squared, the derivative of x squared is 2x, and y cubed is simply sitting there as a constant, and the derivative of negative 2y cubed is 0. Okay, for that matter. So we have plus 0 here, and now at 2 and 1, we simply 3 times 1 squared plus 2 times 1 times 2 squared. I'm sorry, 2, 1. 3 times 2 squared, 2 times 2 times 1 squared. So we are looking at 4 times 3, 12 plus 4. Well, that will be 16. So the rate of change at this point, 2, 1, with respect to x only, is 16. What does it mean? It means that as we change the value of x by 1 unit, the value of z will change by 16 units. If you remember what's the interpretation. We'll talk about interpretation in a moment. Del f del y. Thank you. Del f del y, let me look back at the function. Now we're going to differentiate. So the derivative of x cubed is 0, and then the derivative of x squared y cubed is 3y squared x squared, or I'll write it as 3x squared y squared, and the derivative of negative 2y squared is negative 4y. And del f del y evaluated at 2, 1 is 3 times 2 squared times 1 squared minus 4 times 1. So we are looking at 12 minus 4, or 8. Again, the interpretation is if we change, if we take that function f of xy and we change y by a little bit, then the change will be, for each unit of y, we'll have 8 units of z. And increase, because both are positive. Okay? So let's talk about geometric interpretation. Of the partial derivative. So suppose z equal f of xy represent a surface. S. Okay? Such that a point P equals ABC on the surface on S is C equals f of AB. Okay? So what does it mean? Okay, and let's sketch something like this. So, well, let's pick up a generic surface. So this is a surface S. Okay, remember, given by z equal f of x, y. So when x equals a and y equals b, then you have this point which is a, b, c. This is the point P. Okay. And what does it mean taking the derivative with respect to x? It means that we're going to approach this point on a tangent line that is parallel to the x-axis. So it will be this line. Okay. So this line, it's a line on a vertical plane, if you think about it. Well, let's call it t sub x. And this is the tangent whose slope is the partial derivative with respect to x. Likewise, the partial derivative with respect to y give you another tangent line. We'll call it t sub y. And the partial derivative is the value of the partial derivative at this point is the slope of this tangent line at this point. So let's write a comment, and we're going to say that the slope of the tangent line t sub x is given by del f del x evaluated at AB. Okay. Likewise, the slope of the tangent line t sub y is given by the other partial derivative del f del y evaluated at AB. Okay. Again, notice that both tangent, one is parallel to the x-axis and the other parallel to the y-axis. So you can see, if we look at t sub x, the value of y is held fixed, and this is y equals b, right there. Okay? So we approach along this line, and it's parallel to the x-axis. Likewise, if we hold the projection of ty on the x-axis will be on something that is x equals a, and ty is parallel to the y-axis. The other interpretation is the as rate of change, or instantaneous rate of change. So let's write a comment on this one. Partial derivatives as instantaneous rate of change. This is a little bit shorter. We're going to say that if there is a function, suppose z equals f of x, y, then del z del x equals the instantaneous rate of change of z with respect to x, and del z del y will be the same thing with respect to y. Okay, so going back to the humidity and temperature, if z is the heat index, then del z del x or del z del t will be the instantaneous rate of change of the heat index with respect to the temperature. Del z del h will be the instantaneous rate of change of the heat index with respect to the humidity. Okay?